Wisconsin-Madison. I'm Eftychios, and today I'm going to talk to you about the graphics lab. We call it visual computing group because we do many things that do not conventionally fit into what we would consider computer graphics. But anyways, here it goes. There's two of us, Michael Asher and myself. Mike is out of town today, but his students are in town, so I would encourage you to interact with them. By the way, I have a blatant reminder of our graphics lab open house today between 1:30 and 4 o'clock. Just feel free to drop in any time. I'm also going to talk to you in passing about the work by some of our affiliate faculty, specifically Kevin Ponto. But we also have many collaborators in some of these projects, so it's not just two singletons doing all of this. This is typically a very highly collaborative work that involves many individuals. In terms of location, Graphics and Vision Lab, you will find it in the lobby of the Computer Sciences building. The entry point is CS 1347. There's a robotics lab around the corner that our students can take you to. Mike, as I told you today, is out of town. My office is on the 6th floor. I'm looking forward to meeting with you later. Other than the graphics lab that you will see, the robotics lab has some setup for conducting user studies and experimentations with remote or local interactions. And without further ado, because I realized I had probably 5 times as many slides as I should have for the amount of time, I'm going to talk to you a little bit about the kind of research that I'm into. I guess grammatically, you could say that I'm interested in creating computer-generated models of digital humans, digital stuff, digital physical structures, wherever there are kind of like biological materials, construction materials, water, smoke, explosions, all that kind of stuff, especially when it comes to explosions, breakage, and everything like that. That creates very interesting effects. So I'm all about fracture and mayhem. And at the end of the day, even though there is a kind of like visual facade to all of what we're doing, typically the innovation comes when you peel off the layers. There's some very interesting fast math underneath. So it's primarily a question of can you handle kind of like the avalanche of computational and numerical problems that are thrown your way. So I'm going to give you a little bit of a potpourri of things that I have done and so many times kind of like circulate around. So I've been very interested in creating computer models of human bodies, simulating their shape, geometry, function, motion. You can consider applications of that both for movies, games, medical visualization, medical training scenarios. Now, many of these simulations are made more complex if you have non-trivial interactions. For example, you have a swimmer, or if you're messing around with the model that you're trying to simulate, for example, simulations of surgery. I'm going to show you a little bit more. Now, many of these techniques, they can be reused in the simulation of just soft, flashy characters, and there's quite a bit of an application of that in the motion picture industry. This is an illustration of the skinning system that I co-designed with Disney back in 2011. Since Zootopia onwards, this has been pretty much in every soft character that they've had. I have also participated in their system for hair simulation, and moving a little bit beyond from these kind of like visual effects oriented work, I wanted to tell you a little bit of some like the deeper drivers of my work. I have been very interested in using visual illustrations for the purpose of communicating medical procedures and creating training platforms in which people can hone their skills and exercise interesting cognitive tasks without actually having to do it on a real individual. In many cases, it can be simple manipulations of how you cut and expose a tissue flap in order to shorten it, constrict it in a way that is biologically compatible. In many instances, there are significant systems and deployment strategy challenges about that. So we had a surgical training simulator, which we did a pilot deployment over here at the Department of Plastic Surgery. And something that we're working towards these days is a simulator for cleft lip and palate repair. There is quite an interest in this area because this is a condition that affects a vast majority of, a vast segment of the population. It's about 1 in every 450 births in the United States, for example. And the state of educational materials is very low. It's typically just images and some videos. And we're working very hard to have an actual reactive physical simulation system in which surgeons can train and rehearse some of these procedures. Now, it's kind of interesting that the same technology that is used in order to do cutting and suturing and everything like that it has some overlap with things that you can do in order to break things up. So pretty much the same infrastructure that was used in some of these cutting simulations was also used in destruction sequences in movies. Like this is like from Bolt, for example, in kind of like cracking objects or kind of like destruction sequences over there. Moving a little bit towards a different medium, something that I'm very interested in is the dynamics of fluids. The interesting thing about that is that the dynamics of fluids for visual effects purposes creates very interesting animations and visualizations. At the same time, it gives you a very large scale of computations that we need to do, which gives us an opportunity to innovate to the degree that we can in how large of a scale we can accommodate and how fast we can do it. And we will use that in kind of like high resolution simulations of fluids, sedimentary flow, where you have particulate matter immersed in fluids, more cutting, in this particular case in conjunction with collisions. And with that, I want to just bring up to speed on some of the most recent and more wacky things that I have been interested in. So this is an ongoing collaboration with the MIT Computational Fabrication Group. We have what is not probably, certainly the highest resolution system for static topology optimization. It is this technique that says that if you want to engineer a solid structure such that it is as economical as possible in terms of material that it uses, but more optimal in terms of some mechanical properties. So in this particular case, you want to have a suspension bridge that will sustain as high loads as possible on its kind of like flat bed with the least amount of use of material. So you have some of these very highly filamentary suspension designs emerge essentially directly from computational optimization. And right now we have a system that is slightly exceeding the best other demonstration that has ever been done. The difference is that the best other demonstration has been done on a cluster with 10,000 computers, and ours works on a single server, so it's a little bit more economical. I'm interested in complex motion strategies for characters. Here you see a juggler that is performing a dexterous motion based on the action of just the anatomical muscles. And also another interesting facet, which you could consider to be quite orthogonal to graphics, is that I'm very interested in exploring heterogeneous platforms in simulation or just numerical computation in general. So it is no secret that today, if you want to have the maximum density of compute density in a computational platform, a very good option would be to use hybrid CPU-GPU platforms. And it is a dream scenario if you can put your entire simulation just on the GPU or just on a whole collection of GPUs. But many of the simulations that I showed you before, they operate on data sets in the high hundreds of gigabytes. So although they can fit on a reasonably priced commodity server, they will not fit on the GPU memory of even 10x operators if you have them. So that is an interesting opportunity to innovate both on theory and on systems aspects in order to make that happen. Finally, over the years I've been working quite closely with many visual effects studios. I just wanted, just for the sake of telling you about some recent stuff, to tell you about two of my current partnerships. So they're with Weta Digital in New Zealand and Disney Research Studios in Switzerland. On Weta Digital I have been working primarily on facial modeling and simulation, and on Disney Research with facial acquisition and analysis. Now, I wanted to show you some stuff. Unfortunately, you're in the wrong year if you wanted to see anything that I have been doing with Weta Digital. I hope that in 2 years, when Avatar 2 is out, I will be actually allowed to say what we did for Avatar 2. For Disney, it's a little bit more permissive, so I can tell you at least one thing. So one of the projects that we're currently working on, and you see over here, that sometimes requires that you get in funny garb and like put some funny makeup on. So that's my buddy Derek Bradley over there, just 2 weeks before receiving his Technical Academy Award. So they have developed a system for markerless facial capture, kind of like looks like this. So, and one of our projects right now is to take performances that are subject to oscillatory motion like this and filter them so that you essentially get an emotion without these oscillations. And not only that, but actually learn how jiggly your face is. So if you capture the performance of an actor in a studio and you want to recreate it as being galloping on a fictitious horse, you can essentially figure out, based on what you captured, what parts are jiggly and what parts are volatile. Okay, that's all I wanted to say about that. And then I'm going to rush through, give you an overview of what Michael is doing. So Michael's research is straddling several different areas, including human graphics interaction, human robotic interaction, and human data interaction. It's essentially about trying to generate tools and paradigms for facilitating those types of interactions. In terms of interactions with graphics, he has worked in the past with authoring systems based on sketches in order to intuitively craft animations, demonstrate animations of human or articulated body motion by examples, and also work in order to endow virtual characters as this avatar that we have over here with communicative tools such as expressive gaze. And studying what are the opportunities to use gaze as essentially a communicative medium that can create more rapport between the virtual agent, the human agent, and increase communicative outcomes. Now, some of this stuff also pertains to robots, and you might think of robots kind of like from the utilitarian aspects as appliances that do stuff, but they can also be communicative agents. And by the way, this is not just on paper, like we have cute toys like that, and here's Michael petting his robot, like you might be able to see those over there, there bikes them as well. So we have some of these platforms. And from the utilitarian aspect, some of these robots are designed to do assistive tasks. And our objective is to intervene in being able to teach those platforms, control these platforms, essentially remotely use them in the context of collaborations, and also understand what is the intent of the human driver and how this can be translated into an actual action. So lots of that has to do with specifications of actions and objectives via demonstrations, interpretations of what is the user's intent, and then reenaction of that on the robotic platform. In many cases, the user can also exemplify what are the bounds of a robot's capabilities, what are the constraints that it cannot violate, and you can do that with demonstrations as opposed to just kind of like laying out kind of like expert rules. And also, instead of generate some expert kind of like design policies about how to do these kind of things, you can also demonstrate these behaviors. And this is an illustration over here of how this can interface with a remote manipulation platform where a user uses a wand in order to trigger and demonstrate an action, and the robot tries to reenact that. And this can either be done locally or in a remote deployment setting. Some of these actions might also run up the obstacle at the human having different set of constraints as to how they can articulate the limbs when they're performing a demonstration, and those need to be reinterpreted by the robots. And also there's an aspect of potentially simulating those robots before actually building the physical platform, but also simulating them in virtual reality, and also being able to visualize what is the action space. And finally, Michael has been quite active in visualization with perceptual studies, design technique systems, and exploration of paradigms for using visual communication for sometimes unconventional domains such as literature, genetics, biochemists, neurology. One of his most famous works being the visualization of biomolecules and using visualization techniques in order to elucidate their chemical activity and geometrical opportunity for motion. And also use visualization schemes for exploration of genomic data sets, and also even being applied on the corpuses of literature, which we would not necessarily think that it is something that is very easy to directly translate to something that traditional visualization tools would help. Okay, so in the interest of time, I will wrap up here. Remind you that our open house is at 13:47, between 1:30 and 4 p.m. today. And thanks again for coming over. And I would aspire to see you more in Madison.